Welcome to First Spin, a show where I learn how to use the Parallax Propeller without having any prior programming experience. Rather than do this on my own, I have enlisted the help of two experts.
I'm Whisker. I produce a plethora of weekly tech content, and in doing so, the Parallax Propeller is my go-to microcontroller.
And I'm Roy Eltham, and I am doing consulting work with Parallax, and I have several projects and robot kits with Propeller processor.
So now, Addie, you haven't coded ever,
Well, I copied things from a book in high school.
and that's been years now.
Well, yeah, because I didn't know what in the world was going on. I just copied it.
So this really is a fresh view on the whole thing.
Yes. And I have to say, I have never in my entire life had any interest whatsoever in programming.
What makes you interested in it now?
LEDs.
Blinking lights?
I just want the blinking lights to work. So,
Specifically RGB LEDs, right?
correct. There is an RGB LED strip that we were donated, and I was told that I could use the Parallax Propeller to program that, and I was like, okay, for the sake of blinky LEDs, I'll.
Well, this is really kind of cheating on your part then, because
Why
I
is that?
think Roy Eltham is the one who ported the drivers for that RGB LED strip over to the propeller.
I don't know what that means.
Well, I wrote some code to drive them, yeah.
Drive them as in make them work.
Yes.
Okay. So,
to send the signals across the wires to the RGB LED strip to make it go.
gotcha. I can accept that. So yeah. So today, I pretty much sat down and this nice propeller manual was placed into my hands with a lovely cover. I opened it and it just looked like Greek in a bad fashion.
All right, so you have the propeller manual, a nice big thick reference manual.
Yeah, and I just
And
finished the preface. It was a lovely preface.
Now, I know that particular book starts out with sort of describing the hardware.
Yeah, it does. It introduces the propeller chip first, and it mentions this how the propeller has no need for interrupts, and how you can just assign some cogs to individual high bandwidth tasks. I don't really know what interrupts, although while talking to Arduino and prop people, that seems to be the biggest
That
point
is a
of
topic
contention.
that comes up quite a bit, yeah.
Yeah. So I don't know the significance of that.
Well, you go ahead, Roy.
When you have a single core processor like the one on the Arduino, typically you'll have interrupt capabilities built in so that when you're running your main program, if a hardware device that's plugged into it signals something, you need to handle me now, it triggers an interrupt, and the interrupt will cause the processor to switch what it's doing from the main program to an interrupt handler program piece of code, and that will go handle reading the hardware so that it can deal with it in a timely fashion while the hardware is ready to be accessed at that time. And you need to have interrupts when you have a single processor, single core, because you're just running one piece of code and it can only do one thing at a time. And you use the interrupts to handle, like when a serial port has a byte to be received, then you go receive it when it's ready. And then you come back from the interrupt to your main code and keep going.
So it's like a as needed type of thing?
It's based on the like if you have a button hooked up, when you press the button, it could cause an interrupt to occur right then.
Now, so then what happens to the main code? Does it...
Well, what happens is the main processor remembers where it was in the main code, goes off and runs the interrupt code, and then when the interrupt code is done, it comes back and continues where it left off in the main code.
I see. So then what did the cogs do for the propeller?
Well, on the propeller, you just have 8 cogs, and they all run all the time, accessing. They all have full access to all the I/O pins, and they have the ability to individually wait for an event to occur, and when they do, they go into low power state, and then they wake back up when the state changes on a pin or a counter counts up or whether condition you set up. That's another thing that they use interrupts for on single core processors or even other multi-core processors, is that they'll put the processor into like a low power mode, and then the interrupt will wake it up, and it'll respond to the interrupt occurring and do some code and then go back to sleep. So there's those, that's what interrupts are used for. And on the propeller, you don't have interrupts, but you have the ability for cogs to go into a low power wait mode, which is very similar to the other kinds of processors. In order to handle multiple pieces of hardware with the propeller, you can just have a cog for each one interfacing with that hardware, and you don't have to have an interrupt to interrupt the main processor to go read the hardware, because each cog can be reading one or more pieces of hardware itself, and then you can just have one cog that talks to all the other ones and gets the information back from the hardware and does whatever you want the program to do.
So that's like, I mean, would you say then that each cog is similar to a single cog processor?
They call them cores or just processors in other chips. The cog is just sort of Parallax's name to go with the propeller.
Okay.
For a core or a processing unit.
Okay.
And yeah, it has 8 separate independent processing units that are all fully, separate from each other.
That's just a heck of a lot more powerful.
Well, yeah, in some cases. There are other processors out there with a lot of cores also, but they're, sometimes they're more complicated architectures or not, It's just one we happen to really like.
Okay. One of the more subtle things about the difference doesn't have to do with more powerful, but has to do with timing. When an interrupt occurs, it basically puts whatever code was running to sleep. And then it goes off and it does something else. And it comes back. And until that original code has a chance to go around and check the system clock to see what time it is now, it lost time. It has no idea that the interrupt may have been hijacking it for a minute, 10 minutes, an hour, whatever. Yeah. So until it goes about checking the time, it has no idea that the interrupt occurred.
Right. And if you're writing code that's very critical to happen at key times, like if you have a program that every 1 second needs to go off and flash a light or set a value on an external piece of hardware, when you have interrupts going off, your timing for your 1 second can get off because of the interrupt. So you have to go do extra work to make sure your timing stays correct sometimes.
Whereas in the propeller, you can just assign a cog to that.
Right, and the cog has deterministic results.
What's that? What's deterministic mean?
You can predetermine how long a piece of code is going to take very easily by just counting up the instructions and how many clocks they take, and you can get a very fixed amount of time that it's going to take to run that code and have a very accurate result of every X amount of time the code's going to run and work.
So there is a fixed number of clock cycles, I'm guessing? I've heard clock cycles a lot, and
right.
I mean, is that done, I think, by crystals?
Yes.
Yeah, so standard CPU architecture or microcontroller architecture, you have a main central core that, or multiple cores, but they all run off of a clock. Okay. And the clock is, every cycle the clock goes, it causes the hardware to do some stuff internally to execute part of your program. And in the case of the propeller, most of the instructions are 4 clock cycles to execute. So they have internally, it's doing 4 clock cycles, and on each clock cycle, it does another piece of the work.
Okay. Okay.
Um, and then, of course, if you're running on the standard crystal setup on the propeller, you have 80 megahertz. So there's 80 million clock cycles per second. So you can do quite a lot of stuff.
Wait, per second?
Per second
Per
per
second.
cog.
Oh my, per cog?
Yeah.
Right.
Oh my gosh.
So you have 8 times
That's really
that.
fast. Holy
Right.
buckets. Huh.
So that gives you the idea of like the raw power there and why it would be nice to be able to harness every single ounce of that power towards the sort of problem that benefits from having it there. So if you're just writing some code to turn off an LED on, on and off, you don't really need to worry so much about the deterministic timing. So something like a single core Arduino can do that job just fine. But say, for example, you're working on something that is listening to a whole array of different sensors, and it's controlling a whole array of different motors and lights. You don't want to have to take turns talking to each thing.
Well, because you want everything to come in real time.
Exactly.
Right.
Make sense?
Yes, that does make sense. So
Right.
4 clock cycles per cog to do just one command.
Execute an instruction.
And what constitutes an instruction?
So on the propeller, they have what they call PASM, which is propeller assembly language. And that's the actual, low-level assembly code that the processor runs.
Okay.
Some people call it machine code. But so when you're running the processor, it's actually running PASM instructions.
Okay.
And the manual that you have lists all those out and describes what they do.
And do I have to write? Do I write in PASM? Like, does that change anything? Or
You have 2 options with the propeller. You don't have to use PASM at all. They have a built-in spin interpreter. And spin is a high-level language, kind of like BASIC, but it's a little different than that, and it's got a mixture of other things thrown in there to make it a little more powerful than most basics are. And
It's
spin,
unlike a typical BASIC, it's very much designed to go perfectly with the hardware of the propeller.
right?
So in a lot of places it works differently from BASIC, but it works differently in ways that make a lot of sense for the propeller.
I don't really know what basic is, although it sounds like it's supposed to be basic. So, in context, I'm going to assume that basic is simple.
Yeah, well, BASIC is a beginner's all-purpose symbolic instruction code.
Yeah,
It's
an
a
acronym.
a language developed a long time ago that a lot of processors and microcontrollers and whatnot can work with. It's just the thing that people that are familiar with BASIC will see a lot of the same keywords in spin and have similar understanding.
I see.
It's
So-
very easy to approach if you're already familiar with other programming languages because it shares a lot in common with a whole bunch of other ones that are popular.
Okay. So you've got spin and you've got PASM, correct?
Right. Correct.
So then, and you were saying there's a spin interpreter. Now, is this
That's built into the propeller. So when you write spin code, you just download your spin code into the propeller and run it, and it will run it.
So you don't? It's not like something you have to copy paste into every code that you write.
No, it's built into the ROM on the propeller.
Okay. Is that ROM on? Because I think there's a. So you have the 8 cogs, and then you also have the hub, correct?
Right.
So is it on the hub or?
Yeah, well, it's the hub. The hub has shared memory,
Okay.
and it also has ROMs. And when you start up a spin program, it actually tells the hub put a small piece of the ROM into one of the cogs memories and start it running. And that small piece of memory is the spin interpreter.
And does
then
that?
once that cog is running the spin interpreter, it starts reading the main memory and looking for spin code and trying to execute it. and that main memory gets loaded up by the EEPROM when you first boot up the propeller.
To try to simplify what Roy's trying to explain there with the technical terms is the spin interpreter is kind of like a PASM program of its own. That when you give the propeller spin code, it's smart enough to take that program that's built into it, the interpreter, and run that on a cog. And it hands that program that's running the source code that you put into the EEPROM.
And does it take much memory in your cog memory? Like, does it, I know that's a silly question, but if you're copying the spin interpreter onto the cogs, does that take a lot of memory up?
Well, it uses all of the memory of one cog. So each cog has 2K of its own local memory.
Yeah.
And then the hub has 32K of shared memory.
Okay.
So when you load up a cog, you're loading up its local memory with the interpreter, and it runs that code, but it reads the spin code from the shared memory. So you have 32K of memory for which you can write programs in spin and stick them in there.
So even with you just approaching this, you can very easily realize that spin is very human readable. It's very easy to use. But because it has to do it that way, it's very slow compared to just putting your own PASM program into that hub directly, into that cog directly.
Because then you wouldn't end up taking any memory for that spin interpreter.
Yeah. And your program isn't in the main memory. Your program is right on the cog, running right up on the metal.
And full speed.
For the PASM.
For the PASM.
Right. So when you write spin code on the PC in the prop tool, it compiles it into what they call bytecode and puts that into the main shared memory,
which is the 32K.
Right.
Okay.
And then the spin interpreter that's running will read those byte codes and interpret them into the appropriate command that you typed in and execute that instruction.
Okay.
So it takes it a while because it has to read the main memory from the cog, and then it has to look up in a table or do some deterministic logic to figure out what the instruction is that you put in your program.
Wait, you mean read the memory from the main hub?
Right.
Not the main cog.
Right. Well, the main cog the cog running the spin interpreter will read hub memory to read your spin program and interpret it and execute it, do the instructions that you put into your program. And in that process is much, much slower than if you just run PASM code directly.
The short version of that being is that your spin program is not even in the cog.
What do you mean?
The actual bytecode for it is sitting in
the hub.
In the hub.
Yeah, I get that.
And the cogs can only access the hub when the hub comes around and
Okay, so you put your program onto the EEPROM, right? Like it loads, or not even the EEPROM. Can't it load onto, what's the other thing?
It can load it directly into the RAM, into the shared memory of the hub.
Well, isn't that what you would do?
Well, yeah. So when you use the prop tool, there's a few options. One is you can load just into RAM and tell it to run.
Right.
And it will just load it into the hub memory and run it. But if you turn the board off that has your prop on it, it will forget it and not have it anymore. But if you can also tell it to instead put it in the EEPROM, and so then it'll load it into the propeller, and then the propeller will save it to the EEPROM. And then next time the propeller boots, if it doesn't get something from the prop tool to run, it will load its EEPROM and fill up its main memory. It automatically does that.
I see. Okay, so then you load your program into the EEPROM if you want it to stay the next time, or you load it into the main RAM, which is located on the hub, correct?
Right.
And then you have one cog whose 2K memory has the spin interpreter thing, right?
Correct.
That then, I guess, is automatically, automatically starts to to access hub memory to see what it needs to do.
Correct.
Haha. Okay, so then that means you have 7 cogs left to do the other work.
Correct. One of the things that you can do in
Eureka.
spin, one of the things that you can do in spin is start another cog running another piece of spin code.
When would you do that?
Like if you wrote a piece of spin code that would blink an LED at a constant rate, you could put that into a function and then start up a new cog with that code, and that cog will run and blink the LED, and your main program can go off and do something else.
Your main program on the hub.
Right. They're both on the hub.
Okay.
I'm just saying the first one that you started up when you first booted up
cog?
the propeller. Right, the first
Yeah.
cog that was running.
Yeah.
You can issue a command to start another cog running and tell it run that spin code which you've written and put in another part of your file.
So it's like wishing the genie to give you 3 more wishes.
Except that you got 7 more wishes
Ha!
after the first one.
I see.
Because there's 8 total.
Oh, that's kind of cool. Wow, okay.
And just as you can spawn off another cog running some spin code, you could also spawn off a cog running some PASM code that somebody else wrote. There's a lot of folks who have put PASM objects up on the object exchange that are designed to do very deterministic timing driver type of stuff. So like Roy, for example, has written a driver for that strip of RGB LEDs that you want to be able to talk to. I'm sure he probably wrote that in PASM.
Maybe.
Part of it is in PASM, yeah.
And does that spawn off another cog to do it?
Right. Yeah. So the main program runs spin code, but it does spawn a cog with PASM code that actually talks to the RGB LED strip at a low level.
So he can use the spin code as sort of the glue that's easy to work with and easy to organize communication between various things, and he can set off this deterministic timing PASM thing to talk to the very delicate hardware. And it's always just sitting there doing the job, acting as a translator between your simple spin code and the complicated like serial communications that you have to do with some device.
Right. And there's many different examples on the object exchange. There's programs for talking to a servo and communicating with multiple servos, in fact. There's programs for interfacing with a microphone and recording your voice. And there's programs, there's all kinds of objects up there that do all sorts of common things with hardware that you can attach to the propeller that, people have done over the last several years. They put up there and share. So a lot of times when you're starting out a project, you can go look up there and find some code that does what you need to do, like talks over a serial port to an LCD display, or talks to servos, or talks to DC motors, or there's literally hundreds and hundreds of them up there.
So I have a quick question.
Okay.
We're still going back to the cog number 0, I think, because the 8 cogs, they're numbered 0 through 7, correct?
Correct.
So with cog 0, if you want to free up that cog, you write in PASM, right? Maybe?
Well, you always have to use at least one cog.
For
right?
what?
Well, you always have to be using a cog because that's what's actually running code.
Oh, so that cog will always be taken up to, quote-unquote, execute the codes.
Well, a cog. You can actually stop the first cog if you start up another cog to do something, and the processor will still do stuff. If you stop the main cog and you don't start up any others, then the processor is just in standby mode and doesn't run any code.
Because the hub is only accessible. It's not actively doing anything, per se.
The hub does not have a processor.
The hub.
The cogs have processors, And that's a shared resource. The hub is a shared resource that they all get a turn on.
Right. The hub is just fixed logic. It's like a fixed chip that just does some function, and that's all it does.
It's just acting as a train station.
Right. It's just allowing each of the cogs to gain access to the shared memory.
I see.
And it also does some really simple tasks like loading up the first cog with the spin interpreter and running that code.
Okay.
Or it has some other more advanced functions that we'll get into farther down the line for allowing you to do communication between the process, each cog and stuff like that.
All right, we have just a couple minutes left here, Addie. Is there anything else that you wanted to ask before we finished up for today?
Okay, object exchange. And this is actually a question that I've had after you guys have been talking for a while. So a lot of people, they, volunteer their time. They put out these bits of code that allow you to access or do certain things, correct? And why, as programmers, would you not want to do it your own way? Because then you could ensure quality, and you could, like, say you're counting clock cycles, right? To make things as fast as possible. Then wouldn't you rather do it yourself so that you knew where it came from, what it's doing, that it works exactly for what you're doing it?
I think I can feel this. There's nothing stopping you from doing that. Mm-hmm. You, of course, can. And one nice thing about it being most of the stuff is MIT licensed open source is that not only has somebody else provided it, but a large community of very, very clever programmers has also vetted it. They've gone over it, and not only have they gone over it, many times if they've found ways to improve it, they have forked off their own further revisions. So by the time you get there as a new user and you realize you have use for a particular solution, chances are somebody else has already made it, another person has improved it, and then 3 or 4 people have standardized it.
I see.
Right, and another thing is that you can take one of those objects and because it has a source code, you can go over it yourself and make sure it does exactly what you want. And if it doesn't, you can tweak it and adjust it to do what you want.
For example, if you wanted something to run on pins 1 and 2 instead of 10 and 11, very easy to change.
Right. Or if you found a program that talks to servos, but you want to use it for a special kind of servo that needs extra attention, which some of them do. They have feedback and stuff like that. You could start with the one that's up there that will do the basic talking to a servo and add to it to do what you want.
Okay. That makes sense.
Right.
All right. That wraps up our 30 minutes. I hope you found that useful.
Yeah, I've learned a lot, actually. Cool.
Well, that's good.
I dig the cog thing. It's very cool. Well, till next time.
Yep. I'm Whisker.
I'm Addie.
And I'm Roy.
And we hope Addie was able to have a little fun with her first spin.
Yes.